Can you see the screen?
Yep.
All right. So today we're going to be talking about Docker, right? And so it's not going to be, so usually we're talked about Docker in this context in which about Docker as a tool to manipulate images. And so it creates containers for us. We learn about the various commands. So basically, and so we saw Docker as a sort of a black box, right? And we were really always about using Docker, and we had this sort of vague idea what a container is. We just knew that it would somehow isolate our stuff, and whatever we would be running inside the container, it will not be able to see the outside world. It will be as if it is packaged up to its own little box, right? And so that's how we usually saw. And in this today, what we're going to do is we are sort of going to peel away the abstractions. So this box that we see is in just about every Docker presentation. Whichever Docker talk you see, it's going. This box is just going to be there, right? And uh, that's just how Docker is sort of advertised. But today we have to unshackle ourselves from these abstractions and know the one true truth, which is that there is no such thing as a container, at least as far as the Linux kernel is concerned. So the reality really is that the container, there is no such thing as container at the level of the Linux kernel. And actually, what is happening is that there are a couple of features which are together manipulated in certain ways in order to give this abstraction of the container. So when you think about what a container is, let's really sort of concretely define what a container is, right? So the first thing is that the container should have isolation, which is that it should not be able to modify stuff which it's not supposed to. And the first step towards doing that is that you limit the container's view of the world, right? And so this very property of container sort of explains why we need something at the operating system level in order to guarantee this. Because at the if you have any sort of application, think of this thing as this sort of a hierarchy, right? Like for example, a program, it cannot really inspect itself, right? So if you want to inspect a program, you run it in another environment, right? And so when you want to inspect a program, you run it inside a debugger. So the debugger is actually able to analyze the program, since the program is a child of the debugger, but the debugger cannot analyze itself, right? So there's always going to be someone higher up in the hierarchy you need to sort of look into if you want to get this sort of fine-grained control. And on a computer, the primary sort of the one true god of the computer is the operating system, since the operating system is the one that is sort of orchestrating all of this stuff. So a program cannot sort of stop itself. It can only ask the operating system that, hey, I want to be stopped, and the operating system will stop it, right? So this is why I say that there is no such thing as a container, because these things individually they exist in the Linux kernel itself. And so the first thing is which we are going to talk about right now is namespaces, right? So in a computer, there are these various subsystems, right? Like the process ID, the inter-process communication, network, the CPU. These are not all the subsystems, but these are a certain subset of the subsystems. So there are many different subsystems. And so what the Linux operating system provides is the ability to get each process its own virtual view of the system. So as far as that process is concerned, it is the only thing that exists. And so this most fundamental property of the kernel of a container is actually provided by namespaces. So for each subsystem, whether it be CPU or the mount or the network or the interprocess communication, you can sort of create a namespace for that particular process, right? And so for example, if we have the PID namespace, so with the PID namespace, we can actually see what other processes are actually running right now on the container, right? And so what happens is that if you create a PID namespace, then that process is the only process that is on the container. Because what you're doing in the global PID namespace, what is happening is that you have all of the processes. And when you create your own PID namespace for that particular process, then that process is just seeing its own slice of the world, right? So that's sort of what is happening. Now the second thing is that the first thing, of course, the most important aspect is isolation. The second thing is the control of resource usage. Even if the process has just its own section of the world, even if it can edit only one file, still it can wreak havoc on the system by sort of disproportionately using resources. So for this reason, there are C groups at the level of the operating system. So what C groups does is it allows you to do two things. It allows you to sort of view what resources each subsystem is using. The first thing is the monitoring, because when you have a computer on, you're running say thousands of containers on it, you want to sort of have the sort of fine-grained analysis about how much resources each container is using, like how much hard drive capacity or how much CPU power and how much all of the stuff the container is using. And so the monitoring part is done by C groups. And the second thing is that you can actually limit the amount of resources each process is using. So if you think about it, when it comes to allocating CPU time, the operating system uses some sort of scheduler, right? And so the if you set certain limits, like for example, in the C groups, you can set a CPU limit, right? And so then what it will do is it will give time to your this container less often, so that it occupies less time on the CPU. That's one sort of way the C group would work. So and the third thing is the third feature that builds a container is copy and write. Now copy and write is not necessary for a container. The two essential things are C groups and namespaces. So copy and write, basically this is the reason why your Docker containers start up so quickly. So the idea is that whenever Docker sort of creates a container, what it does is it creates this sort of copy and write file system. And so when it creates the container, there is no thing that is actually changing. The file system is completely the same. There is no copying of stuff going on. Only when you need to change stuff does it create a copy of those bytes and then change that particular stuff. So if you, for example, have a container which needs, say, access to a 15 GB folder, for example, and so it does not always copy over the 15 GB folder every time you start the container. It sort of the container sort of gets its own view of that 15 GB, and say if it needs to write 2 3 MB to some particular bytes, then it creates its own copy of those 2 3 bytes and then writes it there. So in this way, most of those 15 gigabytes they are being reused. And so only when the write is the first write is occurring, does any slowdown actually occur, right? And so copy and write is just a way, just there to make this all this stuff a little bit more faster, right? So now let's look at this thing called the process tree, right? So whenever you start the computer, the init process starts, and the init process may basically start other processes underneath it on the tree. Now, the one of the things about namespaces and C groups is that processes sort of inherit the properties of their parent by default, right? So if you would look at it, like for example, if you what you would do is this bash process, it has its own PID namespace, so it cannot see all of these other processes, right? So what will happen is that whenever we create a child process, like for example, the Emacs text editor, it is a child of the bash process. So since it inherits the property of the parent, even the Emacs process is not able to see anything of its parent, right? So the idea here is that as you go down the hierarchy, you can only sort of narrow down your view of the world. You cannot have a broader view of the world. Like for example, the Emacs, it cannot be the case that the bash does not is not able to access all of these processes, but Emacs is able to access these processes. It does not sort of work like that. You can sort of restrict it. You can be equal, but you cannot have more view of the system, right? So if you really look at it in a certain way, as far as bash is concerned, it is the only process in the tree, right? And its child processes are there. So bash is able to view its child processes, and as far as it is concerned, only it is there on the tree, right? So when you think of Docker, right, you consider this Docker to be this one big monolithic tool. And you would be right, since when it was originally created, it was just one big code base. But then they broke it up into different parts. So the first thing is that whenever you interact with Docker through the CLI, it actually communicates with this long running process called the Docker daemon, right? And so whatever sort of instructions you are saying through the CLI, they get delivered to the daemon, which then basically calls upon this thing called containerd. Now, containerd and runc are basically the two parts that do the most heavy lifting. So you can consider the whole container lifetime part to be two parts: the low level part and the high level part. So containerd, what it basically does, is it takes the Docker image, right? And you have this Docker image, and it unpacks it into this thing called the OCI runtime bundle, and it passes this to and does a few more setup stuff which we don't need to get into, and it basically passes this stuff to runc. Now runc needs two things: it needs the OCI runtime bundle, and it needs a root file system, right? So that's how whenever you create a Docker container, it gets its own sort of file system, and within that file system everything is sort of happening. So runc gets the OCI runtime bundle and the what do you say the yeah, the file system from containerd, and it actually runs the container. So runc, this is actually the part that actually runs all of the stuff. So the whole idea behind architecting things this way is to sort of bring some standardization in the community. So the idea here is that you do not have to use containerd, you do not have to use runc, because the protocols that these use, like for example, containerd uses the Docker image, which actually conforms to a specification known as the OCI specification. So basically, the idea here is that no matter which replacement containerd you use, they all follow the same OCI specification. And so this is called open container interface or something specification. And similarly for runc, runc basically all of the standards behind how it is being run are captured by standard. And so anyone who wants to make a replacement to runc, they just need to conform to this specification and they can make a replacement. And in fact, there are various other sort of containerization sort of methods that conform to this specification. So when it comes to making a container, there are only these are the main system calls involved, right? So if you would sort of just go back a little bit to your operating system class, you would be aware of the fork system call. And so when you create a fork, you are basically creating a child process, right? And so the clone system call is the same as the fork system call, but it allows you to specify a few extra flags, right? So using these extra flags, you can, for example, say that this process that I'm creating, that's going to be my child process. It's only going to have, for example, access to the PID namespace, and it is only going to have, it's not going to be able to access anything else. It's not going to be able to access the devices, or it's not going to be able to access the storage or anything else, right? So when you're creating a child process and you want to specify what sort of access it has, then you use the clone system call. And of course, again, you can only go narrower or the same, but you cannot go broader, right? And the unshare system call is, for example, is for the when you want to actually disassociate yourself from an existing namespace. Like for example, I'll just get into why this is important in a bit. I'll also note that down. So basically, what you want to do is, if you don't want to create a child process and you instead want yourself to be in a new namespace or in some new what do you say configuration, then you use the unshare system call. Instead of creating a child, you are able to affect this onto yourself. And the socket pair is basically where the networking part comes in. So whenever you start Docker, right, you usually have some sort of thing where you specify the port mapping, right? You say that on my machine, the 80 port is going to correspond to say 8080 on the Docker container. So you sort of specify this sort of there are two sort of sides to this interface. So whatever calls are coming through the outside world, Docker actually funnels it through to the internal container through this sort of networking interface. And so for that, Unix provides this facility called the socket pair, which allows you to create a pair of sockets that can communicate with each other. And now we have this sort of system called pivot root. Now, for now, let's just consider it to be the same as chroot. So basically what chroot does is, if you will see here, when I say I'll not be able to give you too much of a practical demonstration since I don't have that. I've not done that by myself yet. But basically, if you would see here, you have the root file system, right? So I can basically everything. The at the root of the hierarchy is the root file system, and below that you have all of these folders.
Kishu, your terminal is not visible.
Oh, my terminal is not visible. Okay. Oh, anyways, that's fine. I'm just saying that the root is sort of the base of the file system, and everything, all of the other directories like lib, mnt, home, etc. All of these come below the root, right? But there is nothing above the root, right? As far as the our computer is concerned. So when you are actually rooting into some other directory, right? For example, if you have a downloads folder, right? Inside the downloads, you root into the downloads folder. Then the download becomes the root, and everything below that you can access, but everything above that you cannot go back to, right? So that's how the downloads becomes the maximum upper point limit which you can actually reach, and beyond that you cannot go. So whenever sort of Docker is setting up a container, what it basically does is it sort of basically creates whatever namespaces are needed, and then the final sort of thing is that it pivots root into the containers file system, right? And so the containers file system just becomes the root. So say the containers file system is within some folder, now the container is only able to see everything below that folder, but it cannot see anything above that. And now the setns is another system call. So basically, whenever you're doing clone or unshare with these sort of system calls, you're basically creating a new namespace, right? And so these namespaces, if you just don't want to create a new namespace and instead want to sort of reuse an existing namespace, so for that you use a setns system call. Now let's talk about the runc, the runtime that actually runs the container, right? So what when I actually looked at the runc source code, it does a few things a little bit in a weird manner, right? So basically what it does is, the first thing is, it creates a fork of itself. It actually runs a fork of itself. So instead of typically when I expected it to run a container, I thought that there'll just be one fork, and that fork will be the child process, which will be the container process, and then the container will start running. But actually the actual container creation is a little bit more complicated, and we'll get into why in right now, right? And so first of all, it creates a clone of itself, and it starts itself from itself, right? That's the first part, and I'll just show you where in the code that is happening. And basically the whole runc runtime is actually written in Go, except for these two crucial parts which are actually written in C, right? And so the third thing is that the runc runtime, it does not actually unshare all of the namespaces you specified once. Now, typically, what would you expect? Say the user says that, hey, I want this to access only its own PID, only its own mounts, only its own devices. Then you typically expect that all of that stuff will happen together. But there it follows a certain sort of hierarchy, which I'll get into in a second, right? So now let's get into the reasons why it actually. The first question is, why does it actually call itself? What's the reason for creating a clone of yourself? So the basic reason is that Go by default is multi-threaded, right? So Go by default, the Go runtime is multi-threaded. So all of this namespace stuff is supposed to run in a single threaded environment. So what they basically do is, and I found this very interesting, they do this sort of hack. So just confirm whether you can see my text editor. You cannot see, right? So I'll just reshare my screen. Can you see the text editor now? Yep. So, okay. So they basically use this sort of a hack, which I consider to be a hack. So if you would see here, right? So there is when this is actually everything is written here in a comment, right? You can see that this is written in a comment. But actually there's something called cgo. What it actually does is it considers this to be flags, and it actually executes this function. So this is sort of a, I think, a hack to basically run some code before the go runtime starts up. So this function ns exec, this is actually a C function that it is calling. And I'll just show you what the C function looks like. So this is the C function. And of course, as we come into C, it becomes a little bit ugly. But anyways, um, right. So here, yeah, this function, it actually executes before the go runtime actually starts up. Right. So let's just look into some general ideas that we can get from this sort of code base that are not specific to Docker. So what actually happens is that I'll just tell you what happens. So we first start run C from the CLI, right? That's the first step. Now run C, after doing all the configuration, creates a clone of itself with a special flag. So it creates a clone of itself with a special flag. And that special flag basically imports this particular file. And whenever it imports this file, whatever this, okay, I have too many files open. Um, right. Yeah, here we are. So it whenever it opens this file, it's going to first, before the go runtime starts, it's going to execute the C function. Right. So now there are two processes. The first one is the run C parent and the run C child. This is the C code and this is the Go code, right? Now, the problem here is that all of the information about what the container should be like, that info is with this. Uh, but what this is the actual process that is actually going to create the container. Uh, my keyboard is a bit loud. Anyways, so what it basically does is there is a pipe between the parent and child. And so as soon as the runc child starts, it basically asks the parent for the instructions. And there is this file format it uses, netlink or something, netlink format, which you don't need to get into. So basically it gets all of the info about the container instructions from the parent, right? It gets all of this information. And now it sorts of goes through this a little bit complicated handoff process. So basically, let's get into the ns exec. Right. Okay. So all of this stuff, it's all fine. So here it is passing from the pipe the configuration. It's all, we don't need to get into the implementation. It's all fine. And now initially it sets up the socket pairs, right? The pair of sockets that are required to communicate. That's all fine. That we don't need to get into that. So now what I found interesting here, I'll just zoom out a bit. Not sure. Wait. Is it still fine? Is it still okay? Yeah. Okay. So right. So you can see here that there is this big comment here. And this author seems to be quite frustrated with how things are the way they are. He actually says, Alexa, what has my life come to? At the end of the comment, because the handoff process, it's a bit complicated, but this is sort of necessitated. So basically, the idea here is that I'll just go back to the PPT, I guess. So basically, now we have this sort of child run C process, right? And so it needs to now create its own child process, right? Again, the run C child process actually creates again a child process of itself. And this is needed because the process that actually unshares the namespaces. So say I'll just go back to the untitled. Yeah. So So this run, if the runc child actually unshares whatever namespaces it has, it all gets its own isolated view of the system. The problem with that is that it is not then able to do some other features that containers offer. So one of the features that containers offer is the ability to sort of map user IDs. So basically, the idea here is that if you have a container, you can be root within the container, but the user who starts the container, he does not need to be root. So within the container itself, within, so basically the idea is a user within container is root. So he's root within the container. He can do anything with the container within the container. Yeah, but of course, since due to the isolation, they cannot do anything outside. But this sort of allows you to create this mapping about what a user is outside the container and what a user is inside the container. So the user can be root inside the container. So for this, creating this mapping, the any process that actually unshares its namespaces, it cannot actually create this mapping properly. So that's I mean, I cannot give you a more in-depth explanation since I don't understand it in depth yet. So basically, that's why it creates another child, right? So it creates another child. Okay, now we have so we have the runc child, we have runc another child. This is also a C code, and so this is basically it's going to unshare the namespace, and this is going to set up UID mapper, right? So so now we have this sort of setup. Now there is still another problem here, which is that if we want to sort of uh, unshare the PID namespace, right? Well, what we need to do is we basically need to create another child. So again, we have another child, C code, and this basically exists for the sole purpose of unsharing the PID namespace. So the Linux kernel is set up in such a way that all of the namespaces can be unshared within the current process, except the PID namespace, which only comes into effect if you create a child. So you can unshare the PID namespace, but until you create a child, that child is the only one that is going to be in this new PID namespace. So because the PID is the only one that sort of creates a problem in which if you sort of the program is thinking that say I am PID 1234, and while running itself, its PID changes to 1 because it unshared its namespace. That sort of causes problems with a lot of programs. So basically, the Linux kernel only allows a new process to start with the PID namespace. So that's why there's this hierarchy. So each child did not make this needlessly complicated. This was just the way it was needed. So basically, there is this thing. Now this is all fine. This is all fine. But what I found interesting was how they are basically communicating and synchronizing all of these processes, right? So they use this. I learned a few new system calls for this. So basically, they use this one big switch case state machine, right? And so basically, they have these various sort of numbers, special numbers, which they use to various states, basically. So basically, what is happening is they are using this thing called set JMP. So basically, this is sort of a way to, and I guess it was there above also. Let's go over there. It's been a little bit of time since I yeah. So basically, this is how you create an environment variable apparently within C, in which you basically are whenever you create a process, you basically let it know about what this its environment variable is going to be. And so each process it creates, it ends up in a different state, right? And so, for example, this is the jump parent. This is for the parent process. There is the jump child, which is for the child process, and there is finally the jump init. Yeah, this is the grandchild process. Okay, so this is in the final child process. Okay, and so you can see here also that it is using the clone and unshare system call. That we don't need to get into the code, but anyways, so basically And to synchronize these processes, basically the way it is happening is that say the say you want to, for example, ensure that the child process uh, has done B before parent C. So basically, what it does is the before parent say does C, it reads from a pipe. It reads from pipe, and child process, once it has done B, it basically oh, I'm typing what I'm saying. I'm sorry. writes it writes to the pipe, right? So basically, as soon as the parent reaches that stage of C, it tries to read from the pipe. So till the child process had done anything, the pipe will be empty, and so the read from an empty pipe is going to be a blocking system call. So the parent is going to be stuck there till some data is written to the pipe. And when will data be written to the pipe? Once the child process has written something to the pipe, which it will do once it has done B. So while the child process is doing B, it is sort of guaranteed that the parent will not be executing C before that. So that is the sort of thing that it is doing here. You can see here that there are these various synchronizing uh, sort of system calls here. So that's basically how it is sort of happening. So then this is the meat of the code. There's a lot, the code is like a lot bigger. And so all of this stuff is basically going to the various nitty-gritties of the various configuration for the container. But the core, I think the most important part of the code is this I guess 1,000 lines of code in which you are actually forking the process and creating the container, right? And so that's how basically how this whole sort of thing works. And now finally for the resources, you have these two resources. Actually, I refer to a lot more resources which are linked to. So basically, the first one is actually what taught me a lot of this stuff, which is C groups, namespaces, and beyond. And he actually goes into a lot more detail. I just gave you a very high level overview of what C groups and namespaces are. And he actually goes into detail about what each C group does. And you might also be wondering how we actually created new namespaces, right? How do we create new C groups and attach our process to certain C groups, which I'm not sure of yet. I'm not explored yet. But basically for that, you write to some special files, which I'm not aware of yet, so I won't talk about that. And finally, there is this article called the tool that runs your containers, in which he basically sort of does some manual work which container D does. It takes the Docker image, unpacks it, and then runs it using runc, and that gives you a better picture of what's going on. And of course, finally, you have the runc code base, which is a little bit intimidating to explore. So just check out to the earliest commit in which there is no such complexity. It's much more easier. I guess that was the whole code base was around 1,000 lines of code, 1,000 or 1,500 lines of code. So it was relatively easier. Now there is a lot more stuff they have to handle, a lot more standards they have to support. So yeah, that's about it. I guess we peel away a little bit of the abstraction behind Docker, right?